right. Well, good evening and welcome to Monday Night Calculus. My name is Curtis Brown and I'm joined once again by Tom Dick and Steve Kokoska. Really excited to have these two guys here. We are live streaming, well, Tom and I at least are live streaming yet again from the nation's capital here in Washington, D.C. Steve has made the trek back home from NCTM conference, but Tom and I were here for another conference yet again the rest of this week. So really excited to have these guys on here tonight. And no, Steve, I did not do my homework. So
no.
If you ask me any questions, I may or may not be able to answer those live. I'll do the best I can, but
no.
I'm gonna rely upon the chat. That's just normal. And Wanda Burns asked me earlier if I had done my homework, and I had to confess that I had not looked. So, although I did see that you had written me into one of the questions tonight, so I'm looking forward to seeing that.
There's a bonus question with you involved. That's correct.
All right. Well, let's get started.
All right. If you'd allow me to share my screen.
Oh, well, now you're being picky. I need to give you that permission to do that. So let me. Oh, wait a minute. What's going on here? Here we go. Now we can share your screen.
All right. Looks good. Let's see if this works. How about that?
It looks wonderful.
All righty. Well, Curtis, Tom, it's great to be back with you again for another edition of Monday Night Calculus. Tonight we're going to talk about some important theorems in calculus. A lot of these theorems that we talk about tonight are those that you can abbreviate with letters that we understand when we grade the AP Calculus exam. And I think we've got some good problems, Curtis. I hope you can follow along and at least answer some questions along the way. If not, maybe you can get a little help from some of the participants.
I'm going to phone a friend. That's all I can say.
All right. So the first one, we want to see if we can find all the values of A and B such that this function f is continuous everywhere. So this function f is a piecewise defined function, and let's just try to analyze this a little bit, talk about this function a little bit, see where it is continuous, see what we have to worry about. So for x less than 2, it is this rational function. Rational functions are continuous everywhere in the domain. This rational function has domain all reals except 2, but this part of the function f is only defined for x less than 2, so we know we are okay to the left of 2. It's continuous there. Between 2 and 3, we have this polynomial here really in x. Remember that a and b are going to be constants. Polynomials are continuous everywhere, so we're okay between 2 and 3. And for x greater than or equal to 3, once again, we have a polynomial, actually a linear function, because those two constants, a and b, could be combined. And that's continuous everywhere. So what we really need to worry about, as I think about this a little bit more, is what's going on here at these sort of transition points at 2 and at 3. We've got to sort of connect these curves with the correct constants, a and b, so that this function is continuous everywhere. All right, so I'm going to start by taking a look at x equal 2. And let's see, in order to make this function continuous at x equal 2, I'm going to have to take a look at a left-hand limit here. What's happening as x approaches 2 from the left, and the value of the function at 2. So let's see. As x approaches 2 from the left, of this function f, to the left of 2, it's this rational function. And we've actually talked about problems like this in an earlier Monday Night Calculus. We can factor the numerator, and we can do a little bit of canceling. This function right here and this one are exactly the same everywhere except at 2. And so if we'd like to know what this original function is doing near 2, we can ask, what is this one doing near 2? And in order to evaluate that limit, well, that's just direct substitution because, well, that function is continuous. So that limit is 4. Now, that limit has got to be equal to the value of the function at 2. So I'm going to take 2 and plug it into f, and this is an expression in a and b. I need this limit to be equal to this value, so I equate the two. And I did a little bit of simplifying, and I have one equation and two unknowns. So let's hold that aside, and let's see what's happening at x equals 3. Well, at x equals 3, I've got to do something similar. I've got to take a look at what happens to the function as x approaches 3 from the left, and equate that to the value of the function at 3. As x approaches 3 from the left, I don't think we need to do any other simplification here. There's no canceling or anything like that. This is just a polynomial in x. And in order to evaluate that limit, we can use direct substitution. Direct substitution because, well, this function is continuous everywhere. So I plugged in a 3, and if I've done everything correctly, there's an expression in a and b. And if I evaluate f at 3, I've got this. So this is just a little bit more complicated than the first half of this. I equate those two expressions, and I did a little bit of simplifying. Curtis, don't let me make a mistake on this one. And there's another equation involving a and b. So, all right, if I've done this correctly, I've got two equations and two unknowns. And with a little bit of luck, I ought to be able to solve this problem, solve the system for a and b. So here are the two equations, and there are many different ways to solve this system. I guess when I looked at that, I saw that if I multiplied, let's see, the top equation by a -2, then the expressions with the b's would cancel when I added. So this implied arrow, what I did is I multiplied that equation by a -2. Let's see, I think that's correct. And now I'm going to add these two equations. Those will cancel out. On the left-hand side, I'm left with a 2a, and on the right-hand side, I'm left with a 1, and son of a gun, a is equal to 1/2. Now, in order to find b, I can go back to either one of those two equations, this one or this one. I guess I went back to the second one. I'm not sure exactly why. That just looked easier to me. So I plugged in a equal to 1/2, and I solved for b. And b is equal to 1/2 also. So that means that if a is equal to b is equal to 1/2, then this function will be continuous for all real numbers. And that's a neat problem.
So that's a good problem. Steve, one just comment that was made in the chat, somebody talking about the, I guess it was Don, was talking about a continuity theorem, which I suppose this is a demonstration of, although that's maybe not a formally named theorem. Is that true?
Continuity theorem. What does it say? Does it have to do with direct?
I don't know. I really don't. I was just asking that question.
So I would guess that has to do with direct substitution. So the question is, whenever you take the limit, I'm going to scribble a little, Curtis.
Yeah, scribble a little.
As x goes to a of f of x, I'll put a question mark over there. When is that equal to f of a? Well, you can use that direct substitution if you know that the function f is continuous. And I'm guessing that's what she's referring to.
Right, and I think there's also the follow-up is that that would mean it wouldn't be something you would cite, similar in the reference like MVT or IVT or some of these others that you can cite.
That's an excellent question. Tom helped me on this, but I think on the AP free response question a couple of years ago, there was a problem. I think it was a L'Hopital's problem, in which the students had to evaluate the limit of the numerator and the limit of the denominator. And one of those limits involved direct substitution like that. And students had to indicate why this limit was true. They had to state that f was continuous, and therefore I could evaluate the limit that way.
Yeah, I think it was a problem in which the students were given that the function they were working with was differentiable.
Correct. Yep.
So they needed to cite the result that if a function's differentiable, then it's guaranteed to also be continuous. And so that's why they were able to simply compute the limit by direct substitution, as the function they were dealing with was indeed continuous. Also, I have my own conjecture, Steve, that
yes,
the reason that you have this example in your problem set is that so many of the important theorems in differential calculus, the hypothesis of that theorem either involves that you have a continuous function, or you have a differentiable function. Right. So here's a function. What would we need to do to make sure that we have values of a and b that make it continuous? Okay, once we got that, now we have a function that any of those theorems that rely on continuity, this function would be okay with.
This function, yeah. Mm-hmm.
Do you have a little technology for this one, Tom?
Yeah, I do. Happy to.
Okay.
Show that off. So I'll try sharing my screen here, and I think this evening I'll be working with both platforms, but for this particular one, I thought I would use the 84. So I'm going to attempt to share my 84 screen.
Looks
you all
good.
let me know if that's looking okay. Great. All right. So what I wanted to start out with was just to go ahead and go into the y equals menu and actually try to plot this function that Steve was working with. Okay. So as Steve said, it's a piecewise defined function. And we'll need to find some way to handle that. There is a way to enter a piecewise function on the 84. It's under the math menu. So if you bring up your math menu and just scroll down, it's actually so far down it doesn't appear on the list until you scroll down to see, there we go. Right there at the bottom, you see that piecewise. And when we hit enter, it actually asks us, well, how many pieces are there to your function? And you can put in any number of pieces. I think there's some upper limit, but you could actually have 5. One piece. 5. Okay, 5's the upper limit. The default here is 3, which is kind of handy for our particular purpose. So we can go ahead and say, okay, now 3 pieces sound good. And you can see that it has a nice little template where we can put in a formula for each piece, as well as what part of the domain is that piece going to be defined for. So I'm just going to go ahead and enter what Steve had. So that first piece, I think, was that rational function. It was x squared minus 4.
Curtis, while Tom is entering that, may I ask a quick question here on this y equals screen? Mm-hmm. So there are 3 pieces, but currently I may only be able to see 2 or maybe even 1.5. Is there any way to stretch that so that you can see all the pieces?
There's no way to do that right now, Steve. No.
Okay.
But you do see the little arrow there underneath of the equal sign that he's got. Which means you can arrow down and it shows that there's something below the line there that you need to be able to go and see.
Gotcha.
That's
So you're referring to this little arrow under the equal sign says, there's more to see down here.
Okay.
Right.
So for this first piece, I've got the formula for it, but now we need to put in the part of the domain that's good for, and that was for values of x less than 2. So in that slot, I'll put x, and now I need an inequality symbol. So I'm going to get that under the test menu, which was the second shift of the math menu. Oh, there's that less than symbol down there on number 5.
Don't forget about the conditions that you
Yep,
can
I'll be
use
using that
on
on
the
the next
right-hand
beat
side.
for sure. Okay, so for
Mhm.
x less than 2, there we go. So that piece is taken care of. Now this second piece actually involves these, some people call them parameters. They're constants, but they're constants we can change the values of to create different functions. So this was that quadratic, which was a times x squared. And then I arrow over to get out of the exponent. And let's see, the next piece is minus b. Do my alpha b times x. And then a plus 3. And now I arrow over to get into the part of the domain that's going to be good for. And that starts out, it's a compound. It's 2 less than or equal to x less than 3, I think. So I'll put in the 2. But now when I go to the test menu, instead of just the plain old inequalities, I'm going to arrow over to conditions. This is what Curtis was referring to. And this is nice. This really saves us a lot of typing. So you look down there at number 7, that's already got most of what I need. So I'll hit enter for 7. And so I've got 2 less than or equal to x, and x is less than, all I need to put in now is the 3. And that completes that piece. Now I'll arrow down and get to the third and last piece. It also involves a and b. This was our 2x, and then it was a minus a and a plus b. And then the piece that's good for is all the x's greater than or equal to 3. So let me go to the test menu one last time. There's the greater than or equal down there, number 4. And we'll hit 3 there. Okay, so let me enter that. Okay. Now, before I just dive into graphing this and see what I get, thing is A and B haven't been defined, but you should know that on the 84, the letters A through Z actually always have some value stored in them. Now we can store whatever values we want, but they will always have some value stored in them. So I'm going to just quit out of the y equals. And I'll just go ahead and store a couple of values in for A and B. So I'm going to put in like, well, let's say, how about 3? And the store button is right above the on button. I'm going to store that in A. Okay, so 3 has been stored in A, and let me store, say, 2 into B. I'll do 2, store alpha B. Now, Steve did quite a bit of work to figure out what would be the right values for A and B to make this a continuous function. I just picked, let's assume I had done some work, but I made some kind of mistake. What I was going to do is, well, I think I've got these are the values of A and B. A way to check this would let me graph it and see if it looks continuous or not. Okay, so let me go ahead and graph this now. So I'm going to use my zoom decimal window, see what this looks like. So I see the graph, and let's see. Well, there was a lot of action going on between 2 and 3. Looks like a lot of that is out of view. So maybe I'll zoom out. How about that? So let me zoom out, see if I can see what's going on there. Zoom out. And it's asking me, where do I want the center of the screen to be? Well, the origin's still good. Let's see what we get here. Oh, now I see more of what's going on. And I see I definitely have not a very good value for A and B. Okay, so I need to go back to the drawing board and try some other values. Now, what I would like to show, though, at this point is another feature on 84 that's kind of cool, especially for functions that have these parameters in them, that have the constants in them that you would like to maybe change the values of to see what kind of different function results for those different values of the parameter. And this is kind of tailor-made for what's called the transform app. It's built in. It's not like a special program that you have to load in. It's under the apps menu. So I'm going to press the apps key here. And you don't see it right off, just like with Piecewise. It's down there quite a ways. So I'm going to scroll down. And Bob Sims, Sci2, oh, transform. There it is, the transform app. Let me go ahead and enter that. And I actually get this big kind of title screen. And it has some explanation of some stuff that I need to be aware of on this app. Okay, then now this app, you can think of this as kind of providing you with sliders for the 84. Okay. It says for animated graphing, which we're not going to use here, it says XRes is 3. That's the speed up the graphing. That's going to graph a little faster because it's only plotting for every third pixel, but it's going to make your graphs look a little choppier. So it says set XRes equal to 1 in your window if needed. And that's what that'll be the first thing I'll do. I'm going to set the XRes back to 1. Okay. It says press any key, so I'll go ahead and do that. And let me go into the window. And if you look down there, XRes 3, okay, that's that thing that the graphing app, the transform app set that for us. And I'm going to set it back to what it usually is, which is 1. Okay. And now I'm going to, I want to look at the Y equals menu one more time. It's got that very same function we had before, but you'll notice that beside Y1 and Y2, there's a little bit different symbol. These are the two functions that are kind of set up for doing transformations. And you can use up to 4 parameters. They need to be labeled A, B, C, and D. Those are kind of the specific placeholders for parameters. We're using A and B, so we're in good shape there. Mm-hmm. And now I'm going to go ahead and graph. And so we're going to see the same graph we saw before, but I want you to notice down at the bottom, it says A is equal to 3, B equals to 2. That's what we had before. But now we can vary those by using the left and right arrow keys. So for example, if I hit the right arrow key, and notice that the equal sign for A is highlighted. If I hit the right arrow key, let's see, maybe I didn't hit it. There we go. Notice it incremented up to 4. Okay, so now A is equal to 4. We get a new graph. Oh, I see it did hit twice. Let me go down A values, go back to 4. And it's taken a little while to graph. You can see why they did that stuff with the XRes, because each time you change that parameter, it's happened to basically recalculate the entire graph. Okay. And if I want to change over to B, I use the up or down arrow to switch over to the B value. And so I'm going to decrease B by 1 and see what happens. There we go. And you see, for all these values I've tried so far, I've actually tried 4 or 5 different graphs already. None of them are doing the trick. And in fact, now I'm worried because Steve's already told us what the correct values for A and B are. A equals 1/2 and B equals 1/2. And these values for A and B are, they're going by integer values, whole number values. But notice that in the lower right-hand corner, we have a setup here. I'm going to hit the right topmost key here. It says graph, but the location of that says if I hit the graph key, it lets me set some things for this transformation app. Trail off, trail on, we're not going to deal with those, but I could set the values of A and B here. But what I want to do is set the step size. This is set how much it increments up or down. I'm going to put in 0.5 there. We can set whatever we want, but this will let me hit A equals 1/2 and B equals 1/2. Okay. So let me enter that. And then I'm actually going to do a zoom decimal window. And we can see it's kind of off the screen here. Let me set the window, show you some other things. Let's see. I'll tell you what, I'm going to go down to Ymin, Ymax. Let me add 3 to both of those.
And the reason you're doing that, Tom, is to still maintain being able to step in directions and get nice values for X and Y.
Yes, and also kind of move the screen up so I can see where the action was. So it's that spot, it was that interval from 2 and 3 where all the breaks could have happened. So just get that. And by adding 3 to both Ymin and Ymax, I haven't really changed the scaling at all. It's just shifted. Okay, so let me graph one last time here. Now I still got that transform map. And what I'm going to do now is I'm going to set the B value. Let me hit left arrow. And the B value should change to 0.5, 1/2. And now let me go up to the A value and let me decrease it down to 1/2 also. And if Steve's calculations are right, you should see this graph look nice and continuous when we hit those 2 values.
If and only if.
All right, now I'm down to A equals, and let's see. All right. Oh, we need an applause meter, Steve. So you found the correct values, because notice this is now nice and continuous.
I put a little.
We know this is good because for X values greater than 3, we know the graph's continuous there. We know it was continuous for X is less than 2. It was that stretch between 2 and 3 that needed to match things up, and this looks like it's doing the trick. So that's kind of illustrating both the transform app and the piecewise. So I know I've run my mouth here quite a bit. I should turn it back over to Steve here now, unless Curtis, you see any questions that we should try to address.
I haven't seen any questions at all in the chat about that. I did encourage people to get on and get their calculator and try it though.
Okay.
Tom, one more thing.
I will show one last thing here, because the app, because it runs all the time, when you go back to Y equals, oops, I didn't mean to do that. Let me try that again. There we go. If you see up there at the very top, plot 1, plot 2, plot 3, those have to do with statistics plot. But besides that, it says quit app. And when you're done using the app, that is something you want to do, because on the handheld, I think if you don't quit, it's just kind of always running, and it could run down your battery. So I'm going to actually quit that app. At least that's what I heard. So it's not an issue on the emulator, but on the handheld, that could be an issue. So I'm going to quit transform graph, and I think we're good. And I'll go ahead and do a stop share and hand it back over to Steve.
You know, another question that we could have asked, Tom, and something that people could take a look at, is now that we've defined this A and B so that that function is continuous, I wonder where it's differentiable. And
okay.
You could certainly explore that on the graph screen.
Yeah, it looked like it had some fairly sudden change in slope at that place.
Indeed. So that'd be a good one. Okay, well, let's shift a little bit and take a look at another important theorem here in AP Calculus. And we're going to do that by considering some other questions, some other problems. And number 2 says, show that there's a root of the given equation in the specified interval. So, all right, here's the given equation. Log x is equal to x minus the square root of x. There's the interval 2 to 3. Now, you can look ahead a little bit, and you know that I'm going to try to use the intermediate value theorem. But let me just make a comment here, and Tom, don't let me misspeak. There have been problems on the AP exam recently where students have attempted to use the intermediate value theorem, but sort of use it on two separate functions. And in order to use this properly, you have to have only one function, and it must be continuous on a closed interval. So students have tried to make arguments with the IVT involving two functions, and okay, as we read through some of these responses, we believe that the student has the basic ideas, but they're not conveying the intermediate value theorem correctly by first starting with only one function. And here's how you apply it in this case. If there is going to be a root of this given equation, well, I'll bring everything to the left-hand side and set that equal to 0. I've got to find a value of x or determine whether there is a value of x so that that equation is true. So the way to use the intermediate value theorem is to say, well, okay, I'm going to define this function f, and I've got to think a little bit. Is it continuous on that closed interval 2 to 3? Well, let's see here. The natural log of x is, x certainly is, square root of x is on 2 to 3. And I'm just combining here continuous functions via a sum or a difference. So that's continuous on 2 to 3. And now I've got to use a little bit of calculus vision and maybe even my calculator here to try to find two values so that the value of f at one of them is positive and the value of f at the other one is negative. And that may take a little exploration, and that may take a little bit of looking at the graph. Here's what I found. I found that, in fact, f of 2 was a positive value. F of 3 here is a negative value. And therefore, by the intermediate value theorem, f must assume every single value in between. 0 is in between there, and so there must be a value c, so that f of c is equal to 0. Now, this is called an existence theorem. It tells you that there is such a c, that one exists, but it doesn't tell you what it is. Sometimes we have to work hard to do that analytically, and sometimes we can't do it analytically. We just have to go to technology to find that value. So I drew a graph of these two functions, individual functions, and there's where they intersect. There's where there is a root of the given equation. It looks around 2.4 or 2.5, but in this particular problem, I did not find that value c. Let's try one more before we get to a little bit more technology here. Let's do the same thing with e to the x is equal to 3 minus 2x. And let's look at that interval 0 to 1. So let's see. I'm going to bring everything from the left-hand side over to the right. There's my equation. And indeed, is this continuous on that closed interval 0 to 1? Well, let's see. Yeah, the natural exponential is, that's continuous everywhere. Well, all right, 3 minus 2x is just a linear function. So that's just a combination of two continuous functions, and therefore it is continuous. Now, by the way, I'm evaluating this function at 0 and at 1 at those two endpoints, but you know, sometimes we have to search a little bit, find some other values in that interval so that f at one of those values is positive, f at the other one is negative. It turns out that f of 0 is equal to minus 2. I think I did that right. E to the 0 minus 3 plus 0. Let's see, 1 minus 3. Yeah, that's okay. And f of 1 turns out to be e minus 1. And just to make this a little bit clearer, I think that's equal to 1.718. And just as an aside here, a little bit of AP calculus lingo. I know that this bothers some people. But in AP calculus, we usually connect these two expressions with an equal sign, even though they're not equal. And that's just sort of a convenient notation. We understand in this community that when we write a decimal representation, write that with 3 digits to the right of the decimal. And we understand that it's an approximation, but we nevertheless write it with an equal sign. Now, we had a discussion in Washington, D.C., I think, Curtis and Tom, a little bit of equal signs and when they're important. And generally on the AP exam, Tom helped me a little. We don't worry too much about whether the student writes equal or approximately, except when we get to infinite series. We don't want them writing f of x is equal to a Taylor polynomial of 3rd degree. So there we're a little, not picky, but precise. But otherwise, we don't worry about that. Okay, so one of these values is positive, one is negative, 0 is certainly in between. By the intermediate value theorem, there must be a value c, so that f of c is equal to 0. Here's a graph of these two functions, and there's that value of c. Symbolically, I don't know, it looks like it could be about 0.6 or so. Cool. I'm going to do just another couple of little problems, Curtis, and then we'll hand it over to Tom for a little bit more technology. Let's try this one. Show that there is at least one root, and this time let's use technology to find the root. So Tom is kind enough to do an awful lot of technology with technology demonstrations with the TI-84. I enjoy using the TI-Nspire, so I'm going to show you how I used it to find this value of c. Well, here's the expression, and holy Toledo, that looks awfully complicated, but keeping with the same style as the previous problem. Here's my function f, and I've got to see if there is such a value x that makes that 0. Now, I haven't given any interval here. So we've got to search a little. Again, think a little bit here, using some good calculus vision. Let's see if we can find two values so that one is positive and one is negative. So here's what I did. I think it was pretty easy to see that f of 0 was equal to 100. Is that true? Sure, because this part of the expression would be 0, and that would be 100 times e to the 0. Sure, that's 100. I've got a positive value there. And I think if we take a look at f of 100, we get 100 e to the minus 1 minus 100. And let's see, did I do that correctly? Sure. This is going to be less than 100. So when I subtract that, I get a negative value. So I found a positive value, found a negative value. Oh, wait a minute. You're right, Curtis. We got to double check here. Is this function continuous? Well, let's see. This is just a polynomial. That's continuous everywhere. This is an exponential continuous everywhere. So the difference is, so this is continuous everywhere. So by the intermediate value theorem, there must be a value c so that f of c is equal to 0. And let me show you a way to do this on the TI-Nspire and a way to sort of visualize this, sort of confirm my answer. So on the TI-Nspire, I can actually define a function in a sort of a natural way here. We use this colon equal. That's a little different than something we're used to writing by hand. But we need to define a function using colon equal, and there are other ways to do this on the Nspire. I like that method. G prime I define. And what I'm going to do is ask the Nspire to solve this expression. And you can see that little bar in there. I think Tom calls that which. I think of that as such that.
Yeah.
So solve that expression such that 0 is less than or equal to x is less than or equal to 100. Why? Because, well, those are my two values up here that I found, one positive, one negative. And it came back and gave me this decimal approximation, 53.984 roughly. And the next thing I did was graph these two functions. I adjusted the window a little bit and the scaling on both the axes to make this a little bit nicer, a little bit friendlier. And then on the TI-Nspire, there is an intersect option. So I tried that and I got that exact same value, 53.984. I feel pretty good about this. So this is an example where the intermediate value theorem tells me there is such a C, and I was able to use technology in order to find it. I've got one more sort of quick one here that involves an arctangent, an inverse tangent, an inverse trig function. So let's see, can we find or is there a value of x that makes this equation true, and then can we find it? So let's see, as usual, here's my function f. Well, let's see, let's think about that for a minute. Is that continuous? Well, I know the x minus 1 is. That's continuous everywhere. What about the arctangent? Curtis, I'm sorry, I'm not going to leave you hanging there. You got to answer one question for me.
Yeah.
Is that continuous?
Sure seems like it is.
Sure seems like it is. Where is that continuous for 25 bonus points?
What do you mean, where is it continuous? It seems like it's give you an interval that the inverse tangent, arctangent is continuous. Doesn't it stretch from negative infinity to positive infinity? I mean, isn't that what it does?
Well, I don't know what you mean by stretch, but the domain is indeed all real numbers.
Yeah.
And it is indeed continuous for all real. So if I sneak down to my graph here, here's a graph of the arctangent.
Arctan, by the way, I did see that Stephen Beck popped in here and said that the arctan is a very spooky function, and the tangent is continuous, of course, negative pi to pi, or negative pi over 2 to pi over 2.
Right.
But the arctan, because of those asymptotes, runs negative infinity to infinity.
Well, the input is minus infinity to infinity with the arctan, but
Mm-hmm.
it has horizontal asymptotes here, right?
Yeah.
Okay.
Sorry, I was reflecting that. I was
Very good.
doing the inverse there.
All right, I've got to be clever in my choices here, so I had to think a little bit about this. I took a look at f of 0. The inverse tangent of 0 is 0. There's an x equals 0 minus 1, so that's negative. That's a minus 1. And f of 1 is the tangent inverse of 1 plus 1 minus 1, so they cancel. Tangent inverse of 1 is pi over 4, and that's positive. So let's see. We have this function f that is continuous on all real numbers. We have a value where it's positive, a value where it's negative, so there must be a number c between 0 and 1, so that f of c is equal to 0. And in fact, I went through the same exercise here. I defined a function, my function f. I defined the function g. I used the solve command on the TI-Nspire. I got a 0.520. I did the same thing over here on the graph screen. I used the intersect function, and I got the exact same x coordinate. I feel pretty good about that. So we use the intermediate value theorem to show existence, and by using technology, we were able to find that value. That's pretty good. Tom, a little bit with technology?
Sure, but Steve, before you leave this, maybe
Yeah.
we can address a question I think that comes up sometimes, and
Sure.
sure I state this correctly. I'm noticing, Steve, that here you've abbreviated the intermediate value theorem with just IVT.
Correct.
And the question would be, is that okay for students to use that shorthand for IVT? And I believe the answer is yes, that's considered a well enough known theorem that students say exactly what you said here. We will read it as intermediate value theorem.
I agree with that. We understand IVT, we understand MVT, and I think we even accept EVT for extreme value theorem. I don't know if we'll get that far this evening, but we would accept that one. We understand that one. Yes.
That being said, it's painful, but sometimes students misspell IVT as MVT. In other words, they'll say by the MVT when they mean IVT.
Yeah.
And we just can't accept that because we'll read it as mean value theorem.
Mean value theorem.
Correct.
All right.
Correct.
Okay.
Okay.
All right. Yeah, I'll do just a very quick one and get it back to you here in just a
You
second.
know, one other thing, Tom, while we're
Sure, go ahead.
is it is not necessary for the students to actually cite the theorem. If the assumptions are true, they can draw the conclusion.
Mhm.
For example, in this sort of a problem, if they said, well, f of x is continuous, f of 0 is negative, f of 1 is positive, therefore there must exist a value of c between 0 and 1 such that f of c is equal to 0. They don't necessarily have to cite that theorem. We'd like them to, but they don't have to.
Yeah, I was going to say we would certainly encourage them to cite it.
Right. Okay. Sorry, Tom. Here you go.
Oh, no worries. Okay. Okay. All right. So I'm going to, since you showed what that looked like on the Nspire, let me go ahead and take a look at it on the 84. I'll just look at that example you looked at just now. And that was, I think, the arctangent of x and 1 minus x were your two functions. So let me do y1 as inverse tangent of x. And then for y2, let's do 1 minus x. And then let me just go ahead and do a zoom decimal. Get the nice arctangent graph. And there's our 1 minus x graph. And we can see an intersection point between 0 and 1 here. There's a way to calculate that intersection right on the graphic screen. Well, let's look up here at the top menu. The second shift of the trace button says calc. I'm going to do second trace, calculate. And here are things we can calculate. A specific value, a 0, minimum, maximum. Number 5, it says intersect. Sounds good. I'm going to go down to intersect, hit enter. And it says, okay, well, which two curves? So if I had more than two curves up here, it'd want to know which of the two I wanted to try to find intersections of. So I'll go ahead and say, okay, that blue one's the first curve. Yeah. Second curve's red. There's not too many choices here. Okay. And notice what it's asking for now is a guess. So it's looking for some point reasonably close to the intersection point. This is for instances where you might have multiple intersection points, but you're trying to find a specific one. So we're going to arrow over. Notice it's kind of tracing along that red graph, trying to get in that vicinity. Visually, it looks like I'm almost right on an intersection point, but this is really, I can't count on that. So I'll hit enter when I think I'm close to the intersection point, and then it homes in and gives me the intersection point to much better precision. Something that's handy to know for kind of future use, often when we're finding an intersection point of a couple of curves, we might need that value for something else. For example, later on in the course, when we're doing area, we might be finding a region bounded by a couple of function graphs, and we're actually finding some intersection points, figure out our limits of integration. Just want to keep in mind that the x value you see here, as well as the y value, those are the current values stored in x and y. So if I quit the graph, and if I just typed in x, that's that value that I was on. So there's that intersection value, or the x coordinate of the intersection there. Okay. So just want to show that you can get those values. on the graphics screen directly, but you do have access to them. When you're solving an equation, though, on an AP exam, you don't want to be saying, well, I just used the intersect key. Go ahead and show, even if that's how you found the value using the technology, you want to show what equation you would have solved to achieve that value. What was that a solution of? So like Steve had arctangent of x plus x minus 1 equals 0. You can say, okay, I solved this and I found this value, and that would be fine. Okay, back over to you.
In general, they need to show the mathematical setup, right?
Exactly.
So Tom, we don't have to show this tonight, but another way, of course, to get that intersection point is to use the solve feature.
Yes.
On TI-84. Which I don't know, it might be a little bit more cumbersome, I'm not sure, but if you have Y1 and Y2 entered, it's probably not too bad, right?
Yeah.
Sure.
No, that's a great idea. Matter of fact, I thought about having Tom do that demonstration, having those entered into Y1 and Y2, or just typing them directly into that numerical solver. Either way, it works really nice. You set up the boundaries in the same way. You even give the initial guess, and then you can use the solver.
Okay. All right. Well, we're running out of time here, but let me try one more problem. And Tom, if we have the opportunity, we'll look at the bonus question real quickly. And there is one overtime question that we should just mention. Maybe you don't have time to do that on the technology. So here's kind of an applied problem, a particle motion problem that will involve some of these important theorems. So we have a particle moving, or rather a trick-or-treater moving horizontally on a street. So that his position or her position at time t is given by this expression, s of t, it's a polynomial. Where t is measured in seconds and s in meters. I think this trick-or-treater is moving a little too fast, but anyway, here's the position. Let's start out by finding the average velocity of the particle over the interval 0 to 2. Does the particle travel with this velocity at any instant on this interval? That's kind of an odd question, but wouldn't that be a neat way to get this on the AP exam, where we're testing something about particle motion, average value, and one of these important theorems? Well, the average velocity is this expression, and Tom and I were just talking about difference quotients in Washington, D.C. So in general, this is a difference quotient. S of 2 minus S of 0, I went to the polynomial to compute these values, and I think that works out to be 10 meters per second. So let's see, is there some point here between 0 and 2 so that the velocity is equal to that average value? That average velocity, so that the instantaneous velocity is equal to that average velocity. Well, S is a polynomial, therefore it's continuous on R, so therefore it's continuous on the closed interval 0 to 2. It's differentiable on the open interval, and therefore the conditions for the mean value theorem are satisfied. And so there must be a value of C in that interval 0 to 2, so that the instantaneous velocity, v of c, is equal to that average velocity over that interval, 10. I don't know what it is. It's an existence theorem, but we know there must be one. Well, all right, B and C are going to kind of set me up for part D here. Bear with me a little bit. Can we write an expression for the velocity, v of t, velocity of the particle at any time t? Well, sure. That's just the derivative of a polynomial here. So we take the derivative term by term. I guess lots of uses of the power rule here. There it is, 3t squared minus 18t plus 24. And in part C, I'm simply asking, are there any values for which the velocity is 0? Well, in order to answer that, I'm going to try to arrow up first. In order to answer that question, I'm going to try to completely factor this velocity expression. So I factored out first a 3 out of all of those terms. And in that quadratic, I was able to factor a little bit into 2 linear terms. And by the principle of zero products, I know that the velocity is 0 at t equal 2 or at t equal 4 seconds. So let's think about this for a minute in part D. Can we explain why there must be a time t for which the acceleration is 0? And can we find that value? Well, let's see. We know that v is a polynomial. It's continuous. It's continuous certainly on the interval 2 to 4. It's differentiable on the open interval 2 to 4. And therefore, by the mean value theorem, we know that there must exist a value so that v prime of t is equal to that average of the velocity over that interval 2 to 4, so that the instantaneous rate is equal to this average value. And look what happens here. Both v of 4 and v of 2 are 0, so there must be some point, some value of t, where the acceleration, which is the first derivative of velocity, is equal to 0. Curtis, one more question for you.
Okay.
So this special case of the mean value theorem, where we evaluate at the two endpoints and we get 0, has a special name. What's that called? The special case of the mean value theorem.
Where the endpoints evaluate to 0?
Where the endpoints evaluate to 0.
Boy, it's been a long week, Steve.
It's been a long week? Okay, that's rules.
It's really been a long
That's
long week. Rolle's theorem is what Wanda says. Is that true?
And just trying to think a little.
Stephen Beck says it just rolls off the tip of his tongue.
Indeed, it does. That's terrific.
As does Ryan.
All right. And so
I appreciate all of those jokers out there.
Can we find that value of t? We sure can. I think there should be a minus sign in here. I apologize for that. We'll fix that when we publish these. We solve for t and we find that at t equals 3, the acceleration is indeed 0. All right, so there's lots of good problems in here for you to try with your students. This is an example on number 7, which we won't have time to go through here. I'll have to take care of that equal sign too. We won't have time to go through this one, but this has to do with the extreme value theorem. So that if we have a function that is continuous on a closed interval, there must exist an absolute maximum and an absolute minimum value on that closed interval. I generally like to solve these problems with the candidates test. I think that is the most straightforward way to do this. There are frequently problems on the AT exam where we have to find an absolute max or an absolute min or both. And I'd like to suggest that your students do this using the candidates test. If it satisfies these assumptions, if it satisfies these conditions where it is continuous on a closed interval, I would suggest you use the candidates test. Are there other ways to do this? Certainly. But students have a much more difficult time using those other ways as opposed to this one.
Steve, you might say just a little bit about what you mean by the candidates test.
Well, the candidates test means that what we need to do is we need to evaluate the function at the endpoints and all the critical points. And the extreme values must be in that list, those list of candidates.
Yeah.
This bonus question has to do with Curtis. If you don't know, he is an avid hiker. And you can read through this one, but this is a very nice question about climbing up a mountain, climbing down the mountain, and showing that there must be a point on that path where Curtis crosses at exactly the same time of day on both days. It's kind of a cool problem. Involves a little bit of analytical argument, but I like that one. And our overtime problem actually had to do with taking the derivative using technology. So the question had to do with this one. I think it involved particle motion. And I think we were given S of t as this kind of complicated expression, which involved a trig function It involved an exponential function. There's a log function in there, and it's even a quotient. And the first part of this question was simply to find the velocity of the particle at time t equal 2. Well, what I've shown here on my screen is a way to do that again with the TI-Nspire. And what I did is I first defined this function s, and there is a nice template which allows me to find the derivative of this function s such that, there's that vertical bar again, t is equal to 2. And you'll notice I cheated a little bit here. I put 2 with a decimal in there to ensure that the Nspire comes back and gives me the decimal approximation. I believe that is the right answer, but the issue on the Facebook group was that, well, on the TI-Nspire, pardon me, on the TI-84, some people weren't getting that exact answer, weren't getting that answer. And I think, Tom, correct me if I'm wrong, but it had to do with setting the tolerance on that derivative, numerical derivative function. Is that correct?
Yeah, that's exactly correct. So the numerical derivative on 84 actually calculates what's called a symmetric difference quotient, where it takes 0.001 on either side of the value, and then does the difference quotient over that interval. And that's not quite precise enough, but you can, on the numerical derivative, just add an additional argument in classical mode and make that value smaller, like 0.000001 will be plenty accurate enough. So it's just the fact that it's doing it numerically. It's not actually doing a symbolic derivative, but a numerical one. We just need to give it a little bit of boost in the precision.
Okay. So because, Tom, of the nature of the function, sometimes that's not quite enough.
Yeah, this function really fluctuates pretty wildly.
Yeah.
For short intervals, and that was the issue.
Gotcha.
Yep.
Okay.
Yep.
Great. Thank you, Curtis. Thank you, Tom.
Thank you, Steve and Tom. I really appreciate you guys taking the time to join us one more time here this fall. This was a good setup. Sorry I wasn't able to show up in costume this evening. I know that you're both a little disappointed that I didn't have a costume for tonight. But join us here in a couple of weeks. We've got just another couple of these Monday Night Calculuses ready to go. So 2 weeks time, we'll be back here on Monday Night Calculus ready to go. If you are a teacher and have watched all the way through, please email me, curtis@ti.com. I'll put my email in the chat here. And let me know that you watched all the way through, and I'll send you a link to download a certificate for tonight's session. And I'll also probably do some kind of shameless plug for the remaining Monday Night Calculus and pre-calculus sessions. Anyway, I look forward to seeing you all here in 2 weeks, and we'll make sure that these answers get posted up here tomorrow so you guys can use them with your students. Have a good evening, and we'll talk with you in a couple weeks.